In this video on collections in Rust, we are going to learn about sets and heap. A set is a collection used to store only unique elements. This is a set. This is also a set. This cannot be a set. Why? Because this contains duplicates. You can ask that maps also contain unique keys, so that can also be a set. Well, maps are not sets, but because of the property for unique keys, it can be used as a set. However, there is one problem. Insertion and lookup in both maps and sets are almost identical, but the keys in maps also comes with the corresponding values. No matter whether you use it or not, the memory space will be reserved. So the memory overhead of using map as a set is very high, and the lookup time is identical because sets also follow the same hash table architecture like maps. Sets are of two types in Rust: HashSet and BTreeSet. And yes, they are similar to HashMap and BTreeMap. Sets are just sets of unique values, and BTreeSets are sets but store values in sorted order. Let's look at the examples. Declaration syntax for set is as usual like other collections. First, we imported the module and then declaring the set to store i32 values. To insert values into the set, we use the insert method. Now, if we print the set by running, we get all the values printed in the console. We know sets only store unique values. Let's add a duplicate entry and see what it prints. No change in the output. This means that the set only stores if the value is unique and not already existing in the set. We have a lot of similar methods here like we had in HashMap, like contains method to check if the set contains a particular value, get method to get the reference of the value as an option enum, remove method to remove an entry from the set. To know more about these methods, you can check my video on HashMaps. There is a take method as well, which returns the value as well as removing it from the set. So you can imagine it to be get and remove method together. Now, since we are dealing with sets, HashSet in Rust also comes with all the methods for the fundamental operations for sets. Here we have two sets. Set 1 has 3 values and set 2 has 2 values. You can see 20 and 30 are common for both sets, and set 1 contains 10 and set 2 contains 40 as the extra value. This is intentional to show you the different operations. Let's run it and understand what the different methods do. First, we have isDisjoint method. This line means, does set has no values common with set 2? We have 2 values in common, 20 and 30. So the answer is false. In the console also we can see false is printed. Next we have union method. This means that get all the unique values from both sets. That's why we can see here all the 4 unique values. Intersection method returns all the values in set 1 that are present in set 2 as well. Basically returns all the common elements. So we get 20 and 30 printed. This line with difference method means what are the values present in set 1 that are not present in set 2. We are getting 10 because set 2 does not have 10 stored in it. If we reverse the position of the sets, like set 2 difference of set 1, and run it again, now we get 40 since set 2 has 40 which is not present in set 1. Next two methods are isSubset and isSuperset. To understand it better, I am commenting this line for 40 and then run again. Now this line for subset means that are all the values present in set 1 also present in set 2? The answer is no, because set 1 has this value 10 extra. That's why we can see the answer is false. Superset is the inverse of it. So this means that are the values in set 2 also present in set 1? The answer is yes, because both 20 and 30 are also present in set 1 as well. That's why I commented this 40 to explain it better. So basically we can say set1 subset of set2 is equal to set2 superset of set1. If we run it, we get the answer true. Moving on to BTreeSet, it is same as HashSet, only the values stored in it are sorted. Here's an example to declare and store data in BTreeSet. The insertion order is jumbled, but if we run it, we get the output in sorted order. And since sorted, we can predict the first and the last values. So methods like first to get the first value, last to get the last value, pop first to remove the first value, pop last to remove the last value, range to iterate over a subrange of values are also present here. Basically, the rules are similar to B-tree maps, so I would highly recommend you to go and watch that video first. That leaves us with one last collection to cover, BinaryHeap. BinaryHeap is a special kind of tree-like data structure that efficiently finds and manages the most important item and puts it at the top of the tree as root. That's why it is also called a priority queue. The moment you insert a value in BinaryHeap, it finds its position in the tree and places it based on the level of priority. Here's an example on how to use BinaryHeap in Rust. We created a binary heap and added a few values to it and printed it. Notice to add a value to binary heap, we use the push method, not insert. If we run the program, we can see the highest value we pushed is appearing at first. We can get this highest priority value by using the peek method. This will give you a reference to the highest value present in the binary heap. You can also get a mutable reference as well by using the peek mute method. With this, we can get the value as well as change it if we need. I'll use iflet since it returns an option enum, and if the value is present, I'll reduce the priority by 2 points. Now let's run it and see what happens. Initially, the highest priority was 10. And we saw it by using the peek method. Then we reduced the weight by 2. So now 10 becomes 8. Now since 8 fell behind 9 losing the top priority, 9 moves ahead and tops the list. There is a pop method which gets the priority value as well as removes it from the binary heap. Let's try to pop all the values until the heap is empty. While let helps to loop through all the values till we get none. That's why we write sum of priority equals heap.pop and then print the task. Running this program will print all the values based on the priority until all the values are popped. You can see the values are in descending order. Sure, we could write the program like this as well. Here we are checking whether the heap is empty or not by using the isEmpty method. The behavior would still remain the same. Most of the usual methods are also available in BinaryHeap. There are two more methods which might help you to work with it. One is intoVec, which is for converting the binary heap into a normal vector, and the other is intoSortedVec, which is same as intoVec but in sorted order. Since the binary heap always puts the highest priority on top, it is called a max heap. There is another concept called min heap, where the least priority appears first. Rust only provides us the max heap, so to implement min heap, we need to do a workaround. We can use the reverse struct module and reverse every value while it is pushed. Now when we print it, we always get the lowest first. But surely workarounds come with its own caveats, like we get this reverse for every value. So to get the actual value, we need to reverse it again. Now if we print, we can see all the values normally in ascending order. We are done with collections in Rust. We learned about vectors, maps, sets, and heap. Again, these are just to introduce you to the different collections and their methods. But the real learning happens once you start practicing it. We have already learned enough to create small programs or solve algorithmic puzzles. Do practice them. Even if a single person would benefit from my videos, that would mean a lot to me. So share your feedback in the comments and subscribe to the channel. We are not done yet with Learning Rust series for beginners. There are a lot to come, so stay tuned. I'll see you in the next one.